So we're going to look at them graphically and we're going to look at them numerically. We're going to learn how to estimate a limit using a numerical or graphical approach. That means you're going to need a graphing calculator of some sort. You can use an online graphing tool. There's lots of Desmos or other things like that so that you can see the picture of the graph. Learning different ways that a limit can fail to exist. So we got to learn what a limit is to know if it exists or not, and then study and use a formal definition of the limit. All right, so an introduction to limits, here we go. To sketch the graph of this function, and here we have some rational function for values other than x equals 1, you can use standard curve sketching techniques. We can use a table, we can do whatever. At x equals 1, however, we don't really know what to expect. Now, what I'm going to say is whenever you have these rational functions, probably think about factoring. Top numerator is a difference of cubes. There's some cool stuff that we can do here. But that's not the point of this lesson. So to get an idea of the behavior of the graph near x equals 1, you can use two sets of x values, one from the left side and one from the right side. And this is really important for when we get to evaluating limits, right? So we want to talk about the left-hand limit as we approach from the left, the right-hand limit as we approach to the right. Now, as we're putting in values that get closer and closer to 1 from the left side, so we're less than 1 to start with, we see that our y values are going closer and closer to a value, right? And then if we go from the right side, we start a little bit past 1 and we go backwards, right, towards 1. As we go from 1 from the left or the right, it looks like our y values are approaching the same place. And if the left-hand limit and the right-hand limit agree, I guess for you, then we would say the limit at 1 is here, 3. The graph of that function is a parabola that has a hole in it, right? Because we could have factored the difference of cubes and we're left with x squared plus x plus 1. And although we can't equal 1, right, there's a hole at 1. When we go to the left or we go to the right, we come from the left or come from the right, we're approaching the location of the hole, right? And so the limit at f of 1 is 3. We're approaching 3. So that's how we write this. The limit as x approaches 1. That's how we read it. The limit as x approaches 1 of f of x is equal to 3. Or you can say the limit of f of x as x approaches 1, right? Okay. So this discussion leads to the informal definition of limit, not the formal one yet. So if f of x becomes closer and closer to a single number L, I don't know why L, as x approaches c, some point, some constant, right, from either side, the limit of f of x as x approaches c is L. So as long as the left-hand limit and the right-hand limit agree, as long as we're going to the same place, even if there's nothing there, then that's what the limit is. We're going to evaluate the function x. I wish they wouldn't write it here. Here, we got this nice function, right? X over the root x plus 1 minus 1. At several x values near 0. Now, what happens if I plug in 0 here? Well, I get the square root of 1, which is 1. 1 minus 1 in the denominator is 0. Bad things happen, kids, and we have to bail. We can't do that. So we want to find out, what does this look like? Now, probably you haven't done enough math in your life to know what the graph of this thing looks like just off the top of your head. So we're going to look at x values first, numerically, not graphically yet, to see what happens. So we're going to pick values on either side of 0. Some negative numbers that are close, like negative 0.75, negative 0.5, negative 0.25, and then maybe negative 0.1, whatever that is. And then values that are on the other side, 0.75, 0.5, 0.25, 0.1. We're getting closer and closer from the left and the right. So if I put the function in the calculator, now I'm not looking at the graph right now, but I do want to look at the table. And if we go just to the table part, we're going to have, right, 0 is not defined. And we know that on either side, I can't really tell just looking at -1 and 1 what it's approaching. But what I want to do is I want to go to my table, and in the table set, I'm going to hit ask for independent variable. This is kind of nice to do. So if I come down here and I hit ask, now when I go to my table, I can pick values that are closer and closer to 0, right? So I'm going to go, okay, what happens at negative 0.75? Negative 0.5. I don't know why that's weird. It gave me a fraction. Negative 0.25, probably another fraction. Nope. Negative 0.1. Okay, now you might notice negative 0.01. From the left, it looks like we're approaching 2. I mean, 1.5, 1.7. We're just getting closer and closer to 2. If I put in negative 0.001, ooh, it's just rounding it, really. It's not really 2, but it's not going to put all those decimal places, right? So then I'm going to go from the other side, same thing. So 0.75, and this is being far away. After a few tries, you guys really don't need to do this. But as we go closer and closer, right, I am approaching 2 also. 0.01, really close, 0.00001. 2, right? Now it's not really 2, it's just close to it. So on the left or the right of 0, our limit is approaching 2, which is what they show in this table. We can see that we're getting really, really close to 2. Okay, but you can do this on your calculator, and I recommend that you do, and you don't have to mess around with being far away. You can just go right to 0.1, 0.01, and so on, just to see as it's approaching. Now, it's not always going to approach a nice number, so don't expect it to be 2 always. Sometimes we might want to be noticing that it's approaching like 1.96 from either side, and if you don't cut it close enough, you wouldn't see that, so be careful about that. This limit is reinforced by the graph. So we're looking at the graph, and we have a hole in our root function. Now, if you wanted to see the root function simplified, we'd multiply by the conjugate in the numerator and denominator, root x plus 1 plus 1, and get the root out of the denominator, and some stuff would cancel, and it would be a lot nicer to look at. So this looks like root x plus 1 plus 1 with a hole in it at 0. At 0.2 specifically. Okay. So what if we don't have a limit? Well, if the limit fails to exist, there's a lot of reasons why, but at least for right now, we got to think about that left-hand limit and the right-hand limit coming to the same point, right? If they don't go to the same point, then it definitely doesn't exist. So if we're like, oh, we missed, then it doesn't exist. Okay. So show that the limit absolute value of x divided by x as x approaches 0 does not exist. Well, if I plug in 0, I get 0 over 0. 0 over 0 doesn't make any sense. It's definitely not 1. If I pick some values, this is kind of a neat one to look at from a table perspective, because if I pick some values as I approach, or even not even, I mean, from far away, right? Like if I'm just plugging in points arbitrarily here, I don't know if I can get my pen to come up. If I made a table and I was just thinking about this function, if I plug in -3, -2, 1, we'll save 0, 1, 2, and 3, right? So -3, if I put in -3 here, this becomes 3 over -3, -1. If I plug in -2, this becomes 2 over -2, -1. If I plug in -1 divided by, that becomes 1 divided by -1, that's -1. 0, we said undefined, right? We don't know yet. 1 is 1 over 1. That's positive 1. 2 is 2 over 2. That's positive 1. 3 is 3 over 3. That's positive 1, right? So really, we could cut this as close as we want because we're dividing by the same thing. And the only thing on the left of 0 that changes is the sign, right? If I put in negative 0.00001, this becomes positive over negative, and it's just -1 again, right? So the graph, which we're not looking at the graph quite yet, but if you're thinking about the graph here, we have on the right side of things, we're at 1. And on the left side of things, we're at -1. And if we're approaching 0, the two will never meet, right? The left-hand limit and right-hand limit don't agree. So we can't say that the limit exists. Not at 0. The limit will exist anywhere else. We could pick any other number and it would work. But the limit does not work here. All right, let's see what the book has to say. Consider the graph. Oh, we looked at the graph, and there you go. Okay, all the things that we just talked about. All right, now, kids, you're going to get good at Greek if you're taking calculus. Yeah. This is part of your college life, right? You're in a college class now. We're going to learn Greek. So this is delta. Now, capital delta looks like that. That's a cool one. This is lowercase delta, and your book uses it a lot. Okay. So it says if delta is a positive number, then for x values between 0 and something between, it's any positive value between that number and 0, you know that it's going to be either -1 or 1 on those intervals, right? If delta is negative, from negative, this is our interval, right? Any negative value we pick up to 0 is going to be -1. Any positive number we pick after 0 is going to be +1. Just the graph, right? That's all that we're saying. This describes things on the left of 0. This describes things on the right of 0 for any value we pick. Okay. Because x, absolute value of x divided by x approaches a different number from the right side of 0 than the left side. The left-hand limit and the right-hand limit don't exist or don't agree, then the limit doesn't exist. Left-hand limit, right-hand limit don't agree. Okay. Common types of behavior associated with non-existence of a limit. Okay, let's see. F of x approaches a different number from the right side of C than the left side. F of x increases or decreases without bound as x approaches C. Kids, this is an asymptote. Okay, increases or decreases without bound as x approaches C would look something like this. As we're trucking along, it's like, boo, decreases forever. And then on this side, it's like, way, and it increases forever, right? As we approach this value for C, we would say, whoa, my fingers are never going to get to each other. They just went off into infinity. I have the longest fingers in the world. So definitely not, no, it does not exist there. F of x oscillates between two fixed values as x approaches C. Well, we'll have to wait a minute to see what that might look like. Okay, so let's take another look at the informal definition. If f of x becomes arbitrarily close to a single number, then the limit is written as this. Okay, so as we go to the left and right, we get closer to some value L, then it exists. At first glance, this definition looks fairly technical. Even so, it is informal because exact meanings have not been given to the phrase f of x becomes arbitrarily close to L and x approaches C. Okay. The first person to assign mathematically rigorous meanings to these two phrases was Augustin Louis. I don't know. His epsilon minus delta definition of the limit is the standard used today. Here's another Greek letter for us to learn. Let epsilon represent a small positive number. Okay. So all they're saying is, okay, we want to get really close to C, and we're going to, on the x values, we're going to go delta away either side. Okay. So here's C minus delta, C plus delta. So we're, some distance away, and we start trucking towards it. And we notice that on our y values, we're some other distance away that's not the same as delta, even though this is kind of rectangular. Notice, why is this down there? I don't know. Okay, so I guess what we're saying is that we're some distance away in the y values. And then the phrase f of x becomes arbitrarily close to L means that it lies between these two y values. It's like in a band, some above or some below L, the actual y value that we're trying to approach. Using the absolute value, you can write this as f of x minus L This is like y minus, this is a y value for the function everywhere, minus that specific y value is less than epsilon, the difference between those. Similarly, the phrase x approaches c means that there exists a positive number delta such that x lies in either of the intervals, either to the left or the right of that value. This fact can be concisely expressed by the double inequality. This is a formal definition. The first inequality, if we split this up, right, this is like between, so we can say it's greater than this, but less than this. So the first inequality, greater than this, the distance between x and c is more than nothing. Okay, so we know that they're not the same point. The second inequality is that it's less than delta, some distance away from x, or from c. Okay. So here's our definition of the limit, a formal definition. You probably want to write this down if you're taking notes. Let f be a function defined on the open interval containing c, except possibly at c, and let L be a real number. The statement, the limit of f of x as x approaches c equals L, means that for each y value, epsilon that's greater than nothing, bigger away, if we have some distance from our proposed limit, there exists a delta that's bigger than 0 away from our proposed x or c value. Okay. So given the limit, now, kids, this is a line, right? And we know that on the left-hand limit and the right-hand limit would agree. So we're thinking about this conceptually for a second, because I know the definition is a little bit confusing. If we're thinking about a line and we're approaching from the left and the right side, then the limit as x approaches 3 for this line is going to be wherever we're evaluating that, which is going to be what we talk about the next block. So if we were looking at this from values that were close to 3, right? So like 2.9, 2.99, or 3.1 or 3.01, we're going to approach 1. And then we want to find some delta such that the difference between the function and its y value is less than 0.01 whenever we're between there. So the way we do this, we're trying to figure out how close we want to be to that limit, right? And so we find an appropriate delta to try to establish a connection. This is just saying, how far away to the left or the right do I want to be to get within 0.01 of my y value? And so we're going to set this inequality up. Here's the function. This is f of x. And this is L. Ooh, that doesn't look so good. And we're going to simplify. Because the inequality is less than 0.0, this inequality is equivalent to this, we can solve. Okay, so we divide by 2, there's the 1/2 times this, right? Multiply by half. And we get this delta. So we know that between 0.005 and 0, we're going to have an epsilon that gets us to where we want to be. Okay, as you can see in figure 1.13 for x values within 0.005 of 3, the values f of x are within 0.01. So they're just this, to simplify this a little bit for you, this is how close we wanted to be to our y value. This is L, and we wanted to be within 0.01 of L, right? This is C, and we needed to know how close to C do we need to be within 0.01 of L. And we figured out 0.005.